My research was on hydrokinetic renewable energy systems. The research motivation was that fossil fuels dominate world energy production, but there's limited supply of them, and global climate change has increased interest in a transition to renewable, carbon-free sources to displace fossil fuel use and increase energy supply for the future. Research topics include: what is hydrokinetic energy, what is its potential, what technologies are used and how are they implemented, how do permitting, policy, and spatial planning work, what influences turbine power output, and what are the environmental impacts. For a quick overview, hydrokinetic systems harness the movement-related energy of water flows with no dam or diversion, so that makes them separate from traditional hydropower and tidal barrage systems. Here's a barrage system for comparison. The high tide is trapped and released later, similar to a regular dam. Hydrokinetic systems have various technology types. You can have horizontal or vertical axis. They can be helical or propeller-type blades, and the blades can be ducted or left open. They can be suspended from the top or attached at the bottom, and this is an oscillating hydrofoil, which is a whole separate type of technology. For resource potential, in the U.S., the Department of Energy did a tidal study. They looked for high power density over large areas with sufficient depths to put turbines. And the USGS did a river study and found that hydrokinetics could provide 1,640 megawatt hours per year, while for comparison, existing dams provide 35,000 megawatt hours per year. For site-specific studies, a project in the Florida Gulf Stream could provide 200 megawatts of power, and one in the Kennebec River on the Maine coast could provide the energy equivalent of the consumption of 150 homes. There's also potential for use in rural areas off the grid, like in Mozambique. They're looking for cheap ways to screen areas for potential, and they're also developing microturbines for low-flow areas. And in Malaysia, they're constructing turbines right in the villages. For government support, it's been varied. Some have facilities to independently assess prototype performance. Some give development grants or facilitate research collaborations between developers and government labs. Cost estimates have varied. One estimate said 15 to 20 cents per kilowatt hour. Another said as low as 8 cents per kilowatt hour, which could penetrate the market in some major U.S. cities. One pilot project example is the Verdant Roosevelt Island Tidal Energy Project, which is in New York City's tidal East River. Some technological challenges include that the blade needs to be strong enough to survive submersion for long periods in corrosive conditions, and there's also potential for small ice particles to build up on the turbines. And finally, you have to find the optimal cutout velocity so that the blade doesn't break, but you also have enough power output. For permitting in the U.S., the Federal Energy Regulatory Commission is the lead licensing agency. They have a special framework for hydrokinetics. You can get a pilot project license and install your device for a short time to carry out studies needed to apply for a commercial license. There are many stakeholders in hydrokinetic projects. A big group is fishermen. They can have limited access, and the dragnets can get tangled in the turbines. So marine spatial planning tries to set up certain zones for certain uses, and interactive stakeholder workshops can help delineate these zones. There are various influences on power output. When you install the turbine, its operation and support structure drag both reduce the area's flow, so as you add more turbines, you don't get a linear increase in energy output. These are the various limits on power output. There will probably be a limit on how much the flow can be reduced for environmental reasons. There's also turbine efficiency and drag, and generator and transmission efficiency. So realistically, you could probably get 2.5% of an area's flow out as electricity. Also, you need to think about flow changes over time for power output. Rivers can have ice coverage, flash flooding, complete dry-ups, or channel migration, and tidal power can vary over timescales from months to weeks to several times a day as the tide flows in and out. For life cycle analysis, you can see that the C-Gen turbine has a lot lower carbon intensity than the fossil fuels and solar PV, and most of the carbon and energy embodied is in the materials and manufacturing stage. Turbines can change flows, which can increase estuary flushing time, accelerate flows on the sides of turbines and rivers, reduce natural sandbanks, and also have far-field effects as far as 20 kilometers away. There are various potential impacts on animals, including on fish. There can be migration impacts like impediment because of blocked sections of channels, or impacts due to electromagnetic effects from the cables, but these effects are uncertain at this time. Adaptive management is a process where Devices are installed and then agencies decide on the required mitigations. It also allows the scientific community to use the pilot project as site-based research. Future issues to research include, are there cheaper ways to get the same CO2 emissions reductions? Who would be liable in a boat exclusion zone if a boat got too close to turbines? Are headland sandbank changes really significant? And are the animal impacts significant? Summary points are that climate change and increased energy demand are leading to hydrokinetic development, and there have been regional and small-scale potential assessments. There have been many pilot projects with government support, but there are still technological obstacles to commercialization. Interactive stakeholder workshops can help facilitate siting consensus, and when thinking about power output, you need to think about turbine interactions with flows, environmental and technological limitations, and since the extent of environmental impacts are unknown at this time, adaptive management may be an appropriate strategy for regulation.